Alright, currently you're watching video E4-p2.10, which is going to be the notes on relative humidity. The learning target for this is going to be talking about relative humidity in terms of the moisture content in the air and how much moisture the air can actually hold depending upon the actual temperature of the air. Alright, we're going to start off first with two terms. They're going to be terms in which you may have heard before, and they're going to be common terms that you're going to see in the coming weeks as we talk more about weather and each of the things that is connected to weather. The first term is going to be humidity. Humidity, especially if you are a female during the summer, this is when your hair kind of just wigs out because of the amount of moisture that's actually in the air. And really what it is, it's the amount of water vapor that's in the air at a given temperature. So during the summer when it's really warm outside and there's a lot of moisture in the air, it's because the warmer it is, the more moisture that the air can actually hold. And hold is in terms, it's not really how much it can contain, but it's just in the space that is the air, how much moisture can be found in the air itself. So this is the time in which you get a lot of humidity, and again for females and maybe even males with a little bit longer hair, your hair starts to frizz out. And then you get absolute humidity. Absolute humidity is dealing with a calculation that deals with the mass of the water vapor. So it's the actual, how much, if you put it on a scale, what is the actual mass divided by the mass of the dry air in a volume of air at a given temperature. So in simpler terms, here's what it is. You take the mass, if you were to put it on a scale, of the water vapor that's actually in the air, divided by the mass of the dry air in a volume that is at a certain temperature. So if the air surrounding us is at the same temperature and you were to take the mass with water and then the mass without water, this would give you what the absolute humidity would be at that given temperature. And that temperature has to be constant and the same for the air that has vapor and the air that has no vapor. Okay, what we're going to do is we're going to take a brief glimpse as to what a meteorologist has to say about relative humidity.
Today dealing with relative humidity, and simply put, the relative humidity is the amount of moisture in the air relative to the amount of moisture the air can hold at a given temperature. So a couple of examples here for you now. Air temperature, for instance, being 75 degrees, say the actual dew point temperature, the temperature at which that saturation occurs, is 52 degrees, makes the relative humidity running at about 45%. In another scenario, it's a little more humid this time around. The air temperature is 75, the actual dew point temperature is 72. This is something you see a lot in the southeast, especially in the morning in the summer times. That makes for a very high relative humidity of around 91%. We'll take a break. We'll talk about the differences in wintertime as well as in the desert locations right after this.
Alright, so let's take the weather.com definition for relative humidity. And what relative humidity is, it's a ratio. So it's kind of like when you take 1 divided by 2, it gives, that's a ratio. And what we're going to do is we're going to take the ratio of the current absolute humidity. So if we go back and take a look at what absolute humidity is, it's the mass of water vapor divided by the mass of dry air that's surrounding us. So when you look at those two, we're taking the ratio of the current absolute humidity to the highest possible amount. So it's how much moisture is actually physically in the air right now divided by the dry amount of air divided by the actual how much could be held within the air that surrounds us. So this is the absolute most that the absolute humidity could be, and we express that as percentage because it's written as a ratio. So as an example, if there was, let's say, 22 grams per meters cubed. So if you had a meter cube box and there was 22 grams of moisture divided by, let's say that the absolute most it could hold was, say, 100 grams in that meter cube box, that would be a ratio of 22%, 22 divided by 100. Now again, this is the most scientific of the definitions. We'll give you some more examples of this type of definition for relative humidity, but this is what it is. It's taking the ratio of the amount of moisture that is found within the actual air divided by how much it could actually physically hold. That is the amount of moisture within the air as well, and it'd be expressed as a percentage. Now that's just one example, and as I said before, we'll give you some other examples as we go along to explain relative humidity in simpler terms, but thought we'd start with the hardest first. Alright, so let's get to a simpler definition, and in your notes, I'm going to pull up your notes for a moment here. And in your notes, you're going to be asked to use the diagram to explain the demonstration in the relationship between relative humidity, given the picture that you see right here with the water vapor. Now, mine are in color, yours are in black and white, but nonetheless, you can at least get a chance to see the diagram itself. So, let me explain to you what this diagram is and how you're going to explain it in this space that's provided for you in your notes. Alright. First of all, let's go back to the definition. Relative humidity is the amount of moisture that the air that is in the air compared to how much it can quote-unquote hold at a given temperature. Now again, the air is not literally holding on to the moisture itself, but nonetheless it's captured within our atmosphere. So at a given temperature. So when the air can't hold the moisture, then it starts to begin to condense, and we know condensation to be the form of dew, as an example, when we wake up in the morning, especially during the spring and even the summer, and we find moisture on the grass. Now, what this diagram is showing you as an example is the following. Pull up color here. First of all, if the temperature outside was 10 degrees Celsius, the amount of water that could be held at 10 degrees Celsius completely fills in the circle, meaning that the amount of moisture equals the space that's available for it to be held within our atmosphere. So that's why it's 100% relative humidity. Because at 10 degrees Celsius, at that temperature, this is the amount of water vapor that can be physically held within our atmosphere, in the space that surrounds us. Now, let's say, for example, as the day starts to warm up, let's say that this was 8 o'clock in the morning, 8 a.m. And as the sun starts to rise and the atmosphere starts to get a little bit warmer, the temperature increases. And as the temperature increases, let's say this is now, let's say 10 a.m. The temperature outside is 20 degrees Celsius now. So it's a little bit warmer, sun's up and rising, and the temperature is increasing. The same amount of moisture exists in the space that surrounds us. As you can see, this ball is the same exact size as this ball of water vapor, just again in the diagram. But nonetheless, as the temperature increases, the amount of space that's available for moisture to be held increases. As temperature increases, the amount of moisture that can be held is increasing. Okay? And as it increases, this is the amount of space, the yellow right here, this is the amount of space that would be left for water to come in and be gathered in our atmosphere. The problem is that the amount of water vapor, this is all it has. This is all the water vapor right here in blue that the atmosphere has in it. So what happens is, as the temperature increases, the amount of water vapor that is currently in our atmosphere is the amount that we had at 10 degrees. The amount didn't change. The difference is the space that we had to hold it did. And because we're dealing with a ratio is how much it is holding divided by how much it could hold. The ratio, as you see, relative humidity starts to decrease. So again, the relationship that I'm trying to kind of pound into you guys is this. As you have this amount of water, and as the temperature starts to increase, the space that we can hold that moisture starts to increase. We have a bigger amount of space. And as that space increases, the water vapor stays the same, and what happens is it becomes a ratio, a division problem. How much water is being held divided by how much it could hold. And because the amount of space increased, so your number is going to drop. Because if, let's say, to give you an example, let's call this a number 2. and the space is 2. Just a number, okay? And I want to see why the percentage drops. The same amount of space is 2 that the water is being held, how much water vapor there is. But the space itself, the yellow area, has increased. So now it's at, let's say, 10. That ratio went from 2 divided by 2, which was 100%, to 2 divided by 10, which works out to 20%. Because the amount of water that was there divided by how much the air could hold potentially has increased, because temperature has increased. The third thing I'll explain, again trying to use it another example, let's say we get to about 2 p.m. and the temperature outside has continued to rise, the sun, clear sunny skies outside, and the temperature has increased now to 30 degrees Celsius. What again happens? As temperature increases, the amount of space that the atmosphere has to hold moisture increases. Okay? Air is less dense, it expands, and has more space to be filled in. As that takes place, the amount of water vapor is still the same. The amount of moisture in the air has not changed. The difference is that the temperature of the atmosphere has. Now, what takes place again is if this was referred to as just, let's say, 2, just a number assigned to how much water is there, divided by the space that it could, how much space could be filled with water. Let's say it now increases to, let's say, 20. And again, the percentage decreases once more, simply because all you're left with is this huge amount of space, and relative humidity is a ratio of how much it could hold divided by how much it potentially could hold altogether. So how much water is being held in the atmosphere divided by how much it could potentially hold. And that percentage now is 10%. So again, if you're trying to explain this in the simplest terms, here's what this diagram shows. It shows as the temperature increases, the amount of moisture that could be held in the atmosphere also increases. We have more space that could be filled with moisture, and that is the space that's here in yellow. However, the amount of moisture that's already in the atmosphere has not changed. It remains the same. And that is this, the water vapor that's blue. The amount of moisture is the same. As the temperature continues to increase, the amount of space that surrounds that moisture is increasing, but the amount of moisture is staying the same. So as that happens, the amount of moisture that the air already has is divided by how much it potentially could hold. And that's why the relative humidity continues to drop, because there's more space that the atmosphere could hold more water, but the amount of water remains the absolute same.